So we're going to pick up with our discussion on chapter 15 today. I know you guys have had a busy week with the 2 homework assignments. Hope all that went okay for you and got those finished up. Any questions on, homework or other things related to the class at this point?
Are we just getting one assignment each week now?
Yes, should be just one assignment per week. So the issue with this class is, I don't know if you guys have looked ahead in the schedule at all, but so the last 2 weeks of the semester is it's Thanksgiving week, and then the week after that finals start. So our last lecture in this class is before Thanksgiving. So it's kind of a rush to, yes, thumbs up, right? So it's sort of a rush to the end in that we kind of have to get some homework assignments in, I think is why there were 2 this week. So there shouldn't be more than, there will not be more than 2 per week, more than 1 per week, I guess I should say. But anyway, yes, this class will be over before we know it. I think this is already like week 9 or something like that. So yes, again, sorry about the double assignment. Hopefully you had some time to get all that finished up. Anything else? All right. Well, yes, again, picking back up with chapter 15. This is sort of following up from chapter 14. In chapter 14 we talked about confidence intervals. If we want to estimate the population mean, we had a way of doing that. Instead of giving just a single value, we gave a range of values. That was our confidence interval. Here in chapter 15 is sort of the other side of the other major theme of this class, which is this idea of hypothesis tests. So confidence interval we use to estimate something. We're estimating the population mean. A hypothesis test, instead we have some claim that we're interested in testing. So again, we make some claim and we want to use data to assess the evidence there. So is there good evidence for our claim, or is there bad evidence for our claim? And like I said, these are kind of the 2 main things that you will see that you will use statistics for later in your careers. I guarantee it. So getting a good sense of what we mean by these things is kind of the goal for this class. All right. So again, reminding you of our motivating example here. This is a claim that we might want to assess. For example, we're maybe imagine that you have a 10-year-old cousin and you're concerned about the amount of time he's staring at a screen for each day. So computer screen, iPad, iPhone, whatever. And we have two possible hypotheses about this situation. So kind of what we're interested in testing here is we want to see if Gavin's screen time is the same as, or it's not different than other children, or maybe is his screen time indeed different than other children. And so kind of those are our 2 ideas, and we introduced this terminology of the null hypothesis and the alternative hypothesis on Wednesday. The null hypothesis is in the blue there is kind of the main point. It's a statement of there's no difference, or sort of no effect. So whatever it is that we're testing, the null hypothesis says there is no difference. Whereas the alternative hypothesis kind of gives us the opposite of the null hypothesis. So this is sort of the thing that we're interested in testing. So on the previous slide we have our 2 claims. One is that Gavin's screen time is not different than other children, and then the other one is that it is different. So it's kind of the opposite of what we said in the null hypothesis. So null hypothesis, alternative hypothesis are kind of giving us we're going to choose one of these 2 things as our final outcome. We're either going to go with one or the other. And then just to note that the alternative can be one-sided or two-sided. So we can be interested in testing, is this thing bigger than something, is it smaller than something, or is it simply different from? So going on with our example here, kind of, I guess I didn't really need to say this again, but again, what I mean by a 2-sided alternative is if we're interested in seeing if his screen time is different from, that's what we mean by a 2-sided. We don't care if his screen time is greater than other children or less than other children. We just want to see, is it different? So that's what I mean by a 2-sided. So this is all from last time still. And again, if we want to translate these 2 things into our formal definitions here, we need to write out what our null hypothesis is and our alternative hypothesis. If we let mu up there equal Gavin's daily average screen time, that's what we don't know, right? We want to say something about that average screen time. So our null hypothesis says that average screen time is the same it's not different from other children, so it's actually equal to 6.1, which that was information that we had from a study that we tested a bunch of other children. And our alternative hypothesis again says that his daily screen time is actually different from other children, so it's not equal to that 6.1 that we found from our study. So again, kind of translating the questions of interest that we have, is his screen time different than other children? Kind of translating that into a null and alternative hypothesis, saying it's not different, and then we're saying that maybe it is different. So, okay, so the usual situation is we have a question that we're interested in, and then we go ahead and collect some data and kind of use that data to answer our question. So we're interested. So we're interested in Gavin's screen time. So we ask his parents to record his daily screen time amounts for a random sample of 44 days. And so for each of those 44 days, his parents record the amount of time he looks at a screen. And we find that the mean was 7.3 hours, and then had some standard deviation. So just from this information, true or false, can we conclude that his average amount of screen time is different from other children? So remember, other children here were 6.1 hours was their average. So true or false? Can we say that his average amount of screen time is different than other children? Is that the answer to our question? Yes. So what if I took a different random sample of 44 days and found that it was an average of 6.2, for example, or 6.3? Could I then say that his screen time was different then? Yes. So it is. So what if I took another random sample and found that it was 5.9 hours per day? Still different, but again, the idea is that different random samples will have a different average here. So just the data in itself, we're going to give a false here. So again, this is maybe a little counterintuitive, but let me say what I mean here is that different random samples So again, if I do this another time, I will certainly get something different than 7.3, but I could get something that's a lot less, or it could be bigger. So different random samples of 44 days will have different mean screen time. And so just this number in itself, we don't want to. So again, this gets at the idea that samples vary. So again, it's okay that if I take a different random sample, I'll get a different number. But I need to sort of formalize how I'm going to answer this question. Just looking at the data in and of itself isn't enough to say yes, it is different, because again, this is just something we got from a sample. So maybe the question to keep in mind is it different enough from 6.1 that we can make a statement about that. So the data by itself is not enough to. So question: what would make the statement true? Kind of nothing would make this statement true, actually. What would make the statement true? I guess the making the statement true is if we were able to look at every single day of the year. So if we were somehow able to get our population parameter that we're interested in here is the average amount of screen time that Gavin has. So if somehow we were able to look at every day of his life, and if that number was different than 6.1, then the statement would be true. So the idea is that we've just taken a sample, we haven't seen the whole population. And so we can't say just from the data that this is true. That's a really good question. Any other? Does anyone disagree with me or have any other objections here? It's too early for objections, I guess. But again, just the main idea is that you don't want to just look at the data and say, well, that number is different than 6.1. Then the answer is yes. So again, keeping the idea that our samples will vary, so we want to think about, is it different enough, is the key idea there. And then just an important note here, when you're setting up your, when you're in the thinking about what your hypotheses are, just to make sure to base it on the question you're interested in, not what the data is telling you. So, okay, so I have a lot more definitions here for us, and this is going to help us to answer that question on the previous page more formally, kind of taking a statistical approach to it. So we have three test statistics. We have three definitions that we'll be talking about here. First is test statistics. Then we have something called p-values, and then something called statistical significance. So our definition here for a test statistic is that that's something we calculate from the sample data, and what it does is it measures how far the data departs from what we would expect if the null hypothesis were true. So kind of our sort of just the usual procedure for a hypothesis test is you start out assuming that the null hypothesis is true, and then kind of go from there. So our test statistic simply measures, again, how far the data departs from what we would expect if the null hypothesis were true. And so if the statistic is a lot bigger than 0 or a lot smaller than 0, then that's going to sort of contradict what we would expect. And again, kind of the key idea down here is that we're going to use the test statistic to figure out how likely it is that the null hypothesis is true or false. So that's what I mean by a test statistic. Too many S's up there. And again, I think so hang with me on these definitions, and we'll when we get to an example, I'll tell you more, or kind of show you more what these things mean. So p-value, this is kind of a weird thing, but I also guarantee you that you will see a p-value some other time in your life. So this is relevant stuff here. So the p-value, which stands for probability value of the test, is, again, it's the probability that the test statistic would take a value that's as extreme or more extreme than what we actually observed. And that's where we compute that assuming the null hypothesis is true. So you can think of the p-value as well, it's a probability, but it tells us how likely that the null hypothesis is true. So formal definition is there, but kind of what you need to have in your head is that it's sort of telling me how likely it is that my null hypothesis is true. Someone asks, is this chi-square stuff? So it could be. That's something I think we're going to get to later in the course. I'm not entirely sure. All right, so that's test statistic p-value. A little bit more with the p-value. Again, so if the p-value is small enough, so again, thinking about the p-value, sort of how likely is it that the null hypothesis is true? So if the p-value is really small, so if the probability that if that probability is small, then the data we observed would be very unusual. So again, p-value is calculated if the null hypothesis is true, so that's a really small value. The data we observed would be very unusual. But on the other hand, if the p-value is not very small, then the data we observed is sort of not that surprising. And so what we say there is that it could plausibly have happened due to sampling variability. If the null hypothesis were true. So kind of how we're going to use this p-value to answer our question. So is the null hypothesis true, or is the alternative hypothesis true? And so for now, just we'll come back to this, but suppose that alpha here suppose that's some number that we're saying is small enough, and we'll discuss what I mean by that in a minute. So again, if my p-value is bigger than that number, so again, kind of kind of in this situation here, if the p-value is not that small, if it's bigger than this cutoff we define, then we'll fail to reject the null hypothesis. So kind of think about that as we're saying that the null hypothesis is true to an extent. So if our p-value is not that small, we'll fail to reject the null hypothesis. We'll stick with the null hypothesis if it is smaller than that alpha value, which we say is small enough. So if on that second line, if the p-value is small enough, then I'm going to reject the null hypothesis and go with my alternative instead. So here we will we'll go with the alternative hypothesis instead. So I don't know, this terminology probably seems a little strange to you. So let me try to kind of frame this in terms of our justice system. I think this kind of provides a good context for what we mean by this. So kind of thinking about how a hypothesis test compares to the justice system. What our definitions here so far, we've talked about the null hypothesis. So in the justice system, that would kind of the analog there is that the defendant, our system is innocent until proven guilty, right? So we start out by assuming that the defendant is not guilty. So we're giving them the benefit of the doubt. That's kind of like our null hypothesis that they didn't commit the crime. The alternative hypothesis is just, again, the opposite of that. So that's when we would say that they are in fact guilty of the crime. So our test statistic, kind of think about that as that's all the evidence that we collect. So again, we're trying to decide if this person is guilty or not guilty. So we go to our data and we collect a bunch of evidence. So that's kind of what the test statistic is doing too. It's going to the data and somehow looking at the information that we've collected. And then the p-value is sort of the how likely it is that the data we got would have happened if the defendant was indeed not guilty. So let's say a person out there is being charged of committing a murder, right? So our null hypothesis would be this person is not guilty. Again, we're going to innocent until proven guilty is how our system works. So we're going to start out assuming the null hypothesis, or assuming that they're not guilty. So then we start collecting evidence, right? And so let's say this murder happened in a building at 10 p.m. on, I don't know, Tuesday night or something like that. So if we start collecting evidence, and the first piece of evidence we get is that this person who's being convicted was near the building at 10 o'clock on Tuesday night. Does that give you evidence that the person committed the murder? Probably not, right? It's maybe causing some question, but we wouldn't maybe say just from that they committed the murder. So what if we also find out that they were with this person when or around the time that the murder was committed? Is that going to kind of push it over the edge? Like, is that enough to say that they are guilty? Again, maybe not. Again, it's getting more questionable, right? So what if we find that this person has the murder weapon? Is that going to be enough to say that they have committed the murder? Well, yeah, probably. So again, it's that idea that as the evidence gets more and more in favor of the alternative hypothesis. So as we collect more information and find that, again, if all that evidence that we collected would not be likely if the person was indeed not guilty. So again, that would be, having that information would allow us to say that they are in fact guilty. So it's that idea that we're collecting information, and how likely is it that information actually occurred if the person was indeed not guilty. So I don't know if that helps at all, but that's kind of a motivating example that we're sort of collecting information and seeing how likely the null hypothesis is with that information. Why do our examples always have to use murder? Why can't it be shoplifting? Great question. Next time I will do shoplifting. That's much more safe. I don't know. Maybe I guess that would probably still be a memorable example. I'm trying to give you examples that will stick in your head. So kind of continuing with our analogy here, when the evidence, so kind of in that last, when we're down here in this last section, thinking about if that evidence is enough to say that they're not guilty. When the evidence collected seems likely, so again, if I have enough evidence to say that this person did not commit the crime, then I would say that they're not guilty. So I would sort of go with the null hypothesis there. This would be like failing to reject the null hypothesis. Whereas on the other hand, if the data I collect seems extremely likely, so again I have all that information about them committing the crime, so is it likely that they didn't commit the crime? Probably not, right? So our decision would be that the defendant is guilty. So this would be like we're going to reject the null hypothesis H0. So of course there's always the possibility that we might have bad evidence or sort of tampering or any of those things, but kind of assuming that we have good information, this is kind of the setup. And I don't know if you think it's weird that we're saying fail to reject the null hypothesis. So we're not saying this is not saying we're not going to accept the null hypothesis. We're going to either reject it or fail to reject it, and that's maybe that doesn't seem like enough of a difference there for you, but again, kind of following the justice system, someone is never declared innocent, right? You're either declared guilty or not guilty. Kind of the same idea here. We're never going to accept that the null hypothesis is true. We're just going to fail to reject it, and because the actual truth may never actually be known, so we can't be for sure that that person is innocent. Any questions on this stuff? Kind of what our terminology is and how it's translating to our hypothesis tests here. Nope, all good for now. All right. So we're getting to an example. So keep holding on there. We need a few more things here yet. So again, we've been talking about this idea of what is likely or what is unlikely or extremely unlikely. And what I'll just tell you is that so a p-value of less than 0.05 is usually considered extremely unlikely. So 0.05, 5% is kind of the cutoff that we're going to go between is something likely, is something unlikely. So what I mean by this is, remember, alpha is that number that we're kind of saying is small enough. So that would mean alpha equals 0.05 is sort of that cutoff number that we'll most often use anyway. It is not uncommon for alpha to be maybe a little bigger than that, or even a little smaller than that. This kind of has a connection to confidence intervals in thinking about the confidence level, right? So remember, we had a 90% confidence interval, 95% confidence interval, 99% confidence interval. You would pick one of those based on how confident do you want to be in your estimate. Same idea here. You can pick a different value for what you're saying is small enough based on based on kind of what you think for the example. So most often we'll go with 0.05 is our cutoff there, but it can be anything, anything that you want. And so to give a formal definition, this alpha value kind of talks about what this idea of statistical significance. So kind of repeating what I said before, if the p-value is small or smaller than alpha, then we will reject the null hypothesis and we'll say that we have statistical significance at level alpha. And so that quantity alpha is called our significance level or level of significance. And again, alpha is just kind of that number that we're saying, is it small enough? All right, so that's our definitions for test statistics, p-values, and statistical significance. So let's talk a little bit more about what wow, that was just a little copy and paste accident, wasn't it? So let's say for this chapter, what are we actually going to use for our test statistic, and how are we going to actually find what these things are? So our test statistic here in this chapter is based on what we've talked about in the previous few chapters. So this should feel a little bit familiar, kind of going back to chapter 14 and also sampling distributions. So again, if we have a simple random sample of size n from a large population that's normal, then we know that this z statistic, which is our usual value here, that has the z distribution, which is the standard normal distribution. So this is our usual thing. We're taking our value, subtracting off the mean, and dividing by the appropriate standard deviation. So what we saw back in chapter 11 was that if our population has mean mu and standard deviation sigma, x bar is going to have mean mu and standard deviation sigma over the square root of n. So again, if we're in the case where our population is normal, then that's sort of all we need to know. We can use this calculation and kind of run with our usual bag of tricks there. But again, of course, we saw in chapter 14 that the population is not always going to be normal. So in that case, we can still use this formula, but we'll have to check our conditions. We need to use the central limit theorem that you guys used a few times in your homework assignment. We can use the same formula, but we just need to check those same conditions that we saw back in chapter 14. So yes, we'll come back to those conditions again. So the slight difference here that is for our test statistic in this for these hypothesis tests, again, if our null hypothesis is that the mean is equal to some value mu 0, then this is going to be our one sample z statistic. So here, let me say that mu 0. I'm not sure if I have that on the next page. This is our hypothesized of the mean. So some new terminology here that whatever number we put in our null hypothesis, that's the number that we're going to use in our test statistic here. So again, we're assuming that we're going to start out by assuming that the null hypothesis is true. So we're going to assume that mu is actually equal to that hypothesized value we give. In the screen time example, mu 0 would be 6.1. So in the screen time example, mu 0 was 6.1. That's our hypothesized value that we're starting out with. So we're saying Gavin's screen time is actually the same as that of other children, so it's equal to that 6.1 that we found from other children. So then the formula is the same. We're just putting in a mu 0 there, mu sub 0 instead of, well, again, here in this situation, we don't know what mu is. We're kind of getting into a more realistic situation here. So we're throwing in the value that we're hypothesizing there for it. So again, mu 0 is my hypothesized value. This slide is not in your notes, but I wanted to kind of just formalize this, that when you're setting up your hypotheses here, the null hypothesis is always going to be this thing that we saw. It's going to be that the mean, at least for this chapter anyway, is going to be that the mean is equal to some value mu 0. Again, null hypothesis assumes that there is no difference, right? So we're saying that the mean is actually equal to this hypothesized value. And then the alternative hypothesis will be one of these three things. So it'll always be one of these three things. Either we want to say that the mean is greater than this hypothesized value, it's less than, or simply it's different from. So in our first example, we went with that one on the far right there, but it could be the other things as well. So the test statistic is always the same, but based on what our alternative hypothesis is, we'll have sort of different ways of finding what our p-value is and how we're going to make our decision. So if your alternative hypothesis is that the mean is actually greater than that hypothesized value, how you're going to pick that out in the problem is using some keywords like more than, or at least, or increased. So if you see that kind of language in the problem, that'll direct you towards this version of the alternative hypothesis. So then remember the test statistic. We're going to take z equals x bar minus mu 0 divided by sigma over square root of n. So then to find your p-value, you're going to find the probability that the standard normal distribution is bigger than whatever that z value you find. So so kind of the rejection region, or what's going to allow us to reject the null hypothesis if our test statistic is really big. So that's if we have the alternative says that the mean is greater than whatever we hypothesize it to be. Similarly, if it's the other way around, if we're saying that it's less than mu 0, kind of the keywords that you'll see in the problem is that things like less than, or at most, or reduced, that kind of language. Remember, the test statistic will still be x bar minus mu 0 over sigma divided by square root of n. So we'll calculate our p-value by finding the probability of being less than that number, and sort of the big negative z values would be kind of what says that we'll reject the null hypothesis. And then finally, for the third one, if we have that that it's simply different from, then you're going to see things like different, or is not the same as, or something like that. So still z is going to again be equal to same thing. But then your p-value, you'll find you kind of want the two tail probabilities. So if your z that you get up there is positive, you're going to find this area up here and multiply it by 2. Vice versa, if your z value is negative, you'll find this area down here and multiply it by 2. Again, because if we're saying the alternative is that the mean is different than this hypothesized value, we don't care if it's bigger or smaller. We just want to see if it's different. So we kind of want to look at both extremes, both ends of the spectrum there, of values that are much bigger and values that are much smaller. Either one of those would allow us to say that the null hypothesis is false. All right, so this is a lot of terminology, a lot of definitions. I think it's finally time for an example, and we'll hopefully show you a little bit what I mean by all these things. Any questions before we move on to that? Yeah.
Why do you multiply 2 by the
So why do I multiply it times 2 there? So remember the normal curve there is symmetric. So if I want the area, my p-value will be both of those, the shaded in red and black areas. So again, you could find each of those separately if that works better for you. but those two shaded in parts are the same. So if we find the area of one of them, we can just multiply it by 2. Yeah, good question. Okay, well let's get back to our example here. So kind of formalizing all the information that we've had so far about this example. So we did a recent study which indicated that the average screen time for children under 12 was 6.1 hours. And again, we're concerned about our cousin Gavin, so we have his parents take a random sample of 44 days and find that the mean was 7.3 hours. So in your notes, it then says with a standard deviation of 2.62. That was a little bit of a typo, and we wanted to say that 2.62 is actually the standard deviation from the recent study. So that's kind of from my population. That's my population standard deviation. So just make that note that this is actually going to be sigma here for this example. So sorry about the typo there. Okay, so that's all my background. The question that I'm interested in is, and we've thought about framing this already a good bit, but what we want to ask is this evidence that Gavin's average screen time is different from that of other children under 12 at the 0.05 level of significance? All right, so let's see what we actually have going on here. So. So again, we're going to kind of start out going very, very slowly through this using our 4-step process. We're going to state the problem that we're interested in. We're going to sort of plan what we want to do. We're going to solve and then make our conclusions. So our first step is to state the problem, and it's kind of just using this question that we have here. So the question that we're interested in is his screen time different from that of other children under 12? So kind of that's again kind of obvious there from the end of the example, but we're just interested in seeing, is it different than other children under the age of 12? Okay, so our plan step of this, how we're going to go about solving this, we first want to write out what our hypotheses are here, which we've already done, but just for being thorough here, let's do it again. Remember that our null hypothesis. Before we do that, let's again write out what mu is equal to. So mu is equal to Gavin's average daily screen time. So again, we said that already. Just wanted to remind you that that's what we're talking about. Mu here is. So then our hypotheses were that the null hypothesis was that mu is equal to 6.1. So it's the same as that of other children. Versus our alternative hypothesis said that mu was different than 6.1. And we put the not equals in there because in the question it says, is his screen time different from that of other children? So again, we'll make a note here that our hypothesized value, mu 0, is 6.1. All right. So that's kind of our plan that we're going to use. We're going to use a hypothesis test, and we're going to have these two hypotheses that we are interested in deciding between. So are we going to go with the null hypothesis, or are we going to go with the alternative hypothesis? Here is the goal. So remember, when we solve in these problems, we need to first the solve step has two parts. So first of all, we need to make sure that we can do. We need to make sure that the methods that we have are appropriate, and then we actually can go ahead and do the calculations. So we have to first check our conditions. And remember, this is, again, the definition was that if we have a simple random sample of size n from a large population with a normal distribution. So is our population distribution here, is the screen time for all other children, have we been told anything about that being normal? So here here's our population that we're comparing it to. It says nothing about being normal, right? So we do in fact need to check our three conditions. Again, we're not told the population is normal, so we have to go ahead and check these three conditions. So does anybody remember from chapter 14 what these three conditions are? Yeah, so do I have a random sample? Nice. What's another one? Big enough sample. Yeah, is it large enough? And then what's the other one? Small enough, right? I need my sample to be just right. Not too big, not too small. So again, these questions pertain to this information, right? So these pertain to the actual information that we collect. So do we have a random sample? Again, yes, we do. So the sample is random. Yes, this is stated in the problem. And again, remember that our sample size is 44. So is our small enough condition says that we want to make sure our sample is not more than 5%. So our sample is less than 20 times that of our population. So 20 times 44 equals 880. So how does that compare to, again, we're looking at Gavin's daily screen time. So how does that compare to all of Gavin's days? Is that less than the span of his life? Well, yes, it is. So 880 days, that's a couple years, I guess, but our population, for him being under 12, maybe think about that. We're okay there. And again, n equals 44. Again, we just need to make sure that that's at least 40, and so that also checks out. So all three of our conditions are okay, and even though our population isn't normal, we can go ahead and use this formula and the calculations anyway. So we're good there. So once we've checked our conditions, we can now actually figure out what our test statistic is. So again, remember we have our z is going to be equal to x bar minus mu 0 divided by sigma over the square root of n. So thinking about what we had, our sample mean from our sample was, again, our random sample for 44 days had a mean time of 7.3 hours. So x bar is 7.3. N again is 44. Sigma, again, we've assumed here that sigma is that 2.62 that we found. And again, mu 0, what we're comparing it to is that of other children, which is 6.1 there. So now it's just a matter of plugging this stuff in, right? So our z is going to equal 7.3 minus 6.1 divided by 2.62 over the square root of 44. If you punch that into your calculator, we'll give you a 3.038. So that's the That's what our test statistic will be. 3.038. So again, before we make our decision again, we have to find our p-value. So again, our z equals 3.04, let's say. So remember our p-value. We want both of these tails is going to be our p-value together. Again, since our alternative hypothesis is not equal to, we need to find the area in both of those tails. So our p-value is going to equal 2 times the probability that z is greater than 3.04. Well, so what that is really equal to is we want the probability that z is less than negative 3.04 plus the probability that z is bigger than 3.04. So again, those areas are the same, so we can just find one of them and multiply it by 2. So again, I'm gonna gloss over the step, but what you would do is you would go to the table A, z table, look up 3.04, and if you look up 3.04, take 1 minus that, you'll get the upper tail value. So I'm going to skip over that step, but each one of these is 0.0012, which is 2 times 0.0012. So our p-value down there is this very small number. So again, remember what we're going to do is use this p-value to say if the p-value is small enough, we will reject the null hypothesis. If it's not small enough, we'll fail to reject. And the number that we want to compare it to is that alpha number that we were talking about earlier. And so what is alpha here in this problem? This thing at the very end tells us that we want our level of significance to be 0.05. So that 0.05 is going to be our alpha value. Remember, alpha is our level of significance for the test. So alpha is going to be 0.05. And so comparing our p-value, well, that's less than 0.05, which is alpha, right? So the p-value we found is 0.0024. That's smaller than the 0.05 that we specified in the problem. And so what does that mean? We're going to reject the null hypothesis, or we're going to fail to reject the null hypothesis? I think I heard it. We're going to reject. Yes, exactly. So because of this thing down here, this means that we will reject the null hypothesis. We're going to reject H0. All right, so again, just like with the confidence intervals, we did our calculation, but we're not quite done. We want to kind of say what that means. So again, because the p-value, which was 0.0024, was less than alpha, which was 0.05, we will reject the null hypothesis. So the important thing here is to say what does that mean? If I reject the null hypothesis, what does that mean? So that means that we're going to get rid of the null hypothesis. We're going to go with the alternative instead. So what we're saying is we're kind of going to be okay with the idea that Gavin's screen time is indeed different. So just looking at the number by itself, as we saw earlier, wasn't enough to say, but because we've done a formal test here, this will be enough to say that his screen time is different. So what our conclusion will be here is that there is sufficient evidence to conclude that Gavin's average screen time is indeed different from that of other children under 12. Different from So again, rejecting the null hypothesis here, what that means in sort of practical language is that means that there is sufficient evidence to conclude that Gavin's average screen time is different from that of other children under 12 years old. So there, we're done. The example is over. This was the first time through it. I know maybe this stuff still feels a little unfamiliar, but we'll look at another example next time. Any question you guys have on the calculations we've done here, or what the point is, or why we're able to make this statement when we couldn't before? Yeah.
So if we had been, like if our alternative hypothesis had just been that it was less than 6.1 or just greater than 6.1, would we have still multiplied by 2?
No. So if, let's see here. So pretend that's not there. So if had been that mu was, let's say, greater than 6.1, then the p-value, then again, remember in that case, we only want values that are big for our z. So in that case, our p-value would have just been the probability that z is bigger than the 3.04 that we found. So it would have been just half of that. Yeah. Good question. All right. Well, pretty much out of time. Thank you guys so much for being here, and thanks for paying attention. Have a good weekend, and we'll pick this up and do another example or two on Wednesday.